Welcome back to the Genius Scale podcast, everybody, where we interview geniuses of the day and we talk about real business challenges and applying that genius. So today's genius is Amarjot Singh, founder and CEO of Skylark Labs AI. I'm going to tell you right now, this is an insane company, and I'm going to do my best for you all, honestly, because this guy's so smart. Welcome, Amarjot.
Appreciate it, Jose. Thank you for having me here.
It's a pleasure having you here. Tell us, Skylark Labs, what is it in your own words so then everybody can really get onto the same page with you?
So the simple way of saying this is Skylark is developing the next evolution of AI, which is self-aware. It knows what it doesn't know, where it works, where it has its limitations. And then it has the ability to improve itself, rewrite its own code. So what it was not good at, now it's able to do well on that after a certain number of tries. And then if you can embed that into different kind of physical assets, be it drones or cars or humanoids, you would lead to digital life forms, which can learn and evolve like humans, leading to a world where digital machines or digital life forms can coexist among ourselves, do what we are doing, hopefully a little better, making our life easy.
That was really well said. Really well said. So many questions here, but I think the key point, the key idea, mental model that I think everybody needs to onboard into in order to properly have a dialogue with you here is this idea of digital life forms. Where did that idea come from? How do you define that?
So I think it's a very interesting idea, right? So if you look back to the 1960s or 1984, where 1960s standard software was there, and how well software does is primarily guided by the rules which a designer plugs into that. And then the software does whatever it is designed to do. And if something new comes, we do a software update. And then after a while, the software works well for the patch for which it was not working before. And if you move forward a couple of years, 1984, the idea was that we don't want to be able to insert all of these rules manually because the world is really big. So you might not be able to come up with enough rules to operate in the real world or most of these domains. So the idea was to learn these rules automatically from data, which was your AI models or deep learning models, where you have a model, the complexity of the model is proportional to the data distribution, which represents the real world, and then it automatically learns those rules and it'll do well than your hand-coded software. But the problem there also is that you hit the boundary which is proportional to the data set you have captured. And if you see something new, your model will either not know what to do or will make a mistake and very confidently will make a mistake, which is bad. And then the answer over there is once a model fails, somehow you find out the model fails, which is either through significant damage. And then after that, you go down this path of gathering data, retraining, redeploying, which takes quite a bit of time. And the idea was how do you actually come up with machines which have the ability to do this thing automatically. In fact, this came out of this program called DARPA's Lifelong Learning Machine, which I was part of during my postdoc at Stanford. And they wanted to make machines which could last forever. And this was born as part of that.
So, I mean, those are some really impressive institutions, I have to say. So if we were to take a step back with using my limited software experience, it sounds like you're fundamentally shifting with this idea of digital organisms, software update lifecycle. It instead updates itself on the go autonomously.
Yeah.
So that embedded, not distant learning, put it on the cloud, put it in a server somewhere, and then access it through APIs, all the rest. It does away with that model to a certain extent, doesn't it? Everything happens locally.
Yeah, absolutely. So this is the way, or this is the path using which you're going to be able to make truly autonomous systems, which live and evolve in the real world without actually having a human in the loop.
That opens up a door, doesn't it? This idea of a self-evolving digital organism without much human intervention. How stable can we expect those updates to be over time? How do we make sure that there are guardrails? Should we make sure there are guardrails? There's almost an entire philosophy, a shift in philosophy that's required in order jump on board and say, this is the path?
I think that's a very interesting concept, right? So this evolution, which is on device, unguided, without any human intervention, can be great but also scary. So I think there's a obvious policy discussion that if a machine is learning something, how do we actually know that whatever it is learning is within the guardrails, philosophy, policy within which we want it to evolve? And then the next thing is, if it is evolving positively, that's a good thing. But how do we know that if it starts to go in the negative direction, it's not going to poison itself? So there are a lot of very interesting questions of the machine deciding on its own that it wants to learn something, whether it's good or not. And the second thing, if someone intentionally tries to poison the machine by introducing certain stimuli, which will make the representation of the machine bad, that will be another thing. So there's so much discussion which can happen on this, but the short answer is yes. The intelligence or the super intelligence which is going to be embedded in these machines has to have some sort of consciousness, awareness that what they're learning is actually meaningful, and we need to figure out how to get there.
So this consciousness, this awareness, is kind of like self-auditing and real-time system that we have to basically start to reverse engineer our own consciousness with that action or auditing step. So is that as simple as saying, okay, stimuli introduced to its input areas, I don't know what sort of input areas because we're talking very abstractly here, right? It then assesses good or bad, and then it allows it in. So there's a layer of cybersecurity, there's a layer of identifying, continually adapting or changing stimuli. I can imagine that nefarious actors in the cybersecurity space can say, well, we already understand what it does, what it classifies as good or bad. Well, what if we start to just introduce volume and then, switch and change it over time? So it has to continually update itself and get smarter and smarter at the same time, autonomously. So how do you make it so that it does do that without software updates or intervention by a human? Or is that going to be required on some level throughout the current generation's deployment?
So I think that's a very interesting question. So if you think about how humans do that, right? Um, Wherever you grew up, your parents told you this is good, this is bad, and those are the sort of the guiding principles you follow in your life. So if your parents said, "Hey, it's bad to steal," you don't steal right now. So these principles in humans are introduced over a period of time, and they're a byproduct of our environment. They're a byproduct of our teachings. So in our digital life forms or this adaptive AI, the machine is adapting on its own from the environment and the stimuli. So that is one kind of learning which happens on device. But there are other devices which are nearby, and there is also a function of collaborative learning which goes on between the machines. So if there's one machine or even a human who said, okay, this is good or bad, and you should not do that, the machine is able to encode that as a guardrail. And when it is deployed in the field, it is able to figure out what to do and what not to do. So there's a component of teaching or learning which happens offline in the lab, and those are the rules, principles, safeguards which you as a machine would take in the real world and try to operate within those frameworks. Now, obviously, there are learning within those guardrails as well. But you just figure out that, okay, I want to do incremental learning to those guardrails or not. But short answer is it knows what is bad and good like a human, which we teach it, and then it tries to operate within that.
Got it. Okay. So maybe a bit of a trick question here then as a follow-up. If we were to look at the past generations of software, let's say closed source software versus open source software. Now, closed source software sounds like this is more of a closed source methodology, but could there ever be a way of integrating the kind of like the open source mass edge case handling that happens with open source into this sort of system? Would that be wise to do?
Yeah, I think it's a very tricky question, right? So there always has been these two communities of open source, closed source. And if you look at the large language models, people would say that a lot of the progress which we have made has come because of llama models, which are from Facebook, which were the early large language models, and then their subsequent models on top of that.
Hmm.
So, so I think it's fine to make these kind of models public when they are in the research phase, and we need everyone to collectively come together and improve these models. But I think whether they are large language models or whether they are models, AI has come to a point where it is more or less stable. So it has moved from your research lab to a production facility, leading to not just the good users of this AI, but also nefarious users. So I think at this point, it kind of becomes important to figure out who's the person using it and how. So I think there might be some forms in which you can make this public, but I think a complete system pushing it out would not be a good idea.
I think so too. On some level, if you're dealing with such sensitive systems like
Yeah.
satellites, like other potential IoT sources or devices on network, it could be really dangerous to make it just open source.
Yeah.
Now, would you say that there's potentially like a middle ground here where you introduce maybe like an IoT swarm type of deployment, and then each individual unit is handling its own edge cases, learning on its own, and then feeding it back to a centralized location that can then deploy a software update or
So
decentralized in some capacity?
so that's how we actually do our so that's how we get to super intelligence using collaborative learning.
Mm,
So all of these machines who have you have taught something, they go into the real world and they say, okay, I know how to walk, but now this is a new kind of environment. It's sand or it's ice. I need to correct myself so that I can walk over there. Now that machine can directly interact with another machine or a couple of machines, and it can say, okay, I have learned how to work in this new environment. Here are the weights for you, so that now you can learn how to operate in this new environment. So that's collaborative learning, right? But
mhm,
this collaboration for us happens within the same domain: walking, humanoid, humanoid, bipedal, which will be sort of about dogs, or let's say a target recognition system, which is recognizing vessels.
mhm,
Now we have a cloud unit, which after a while pulls in the weights of the models, not data, from each of these edge nodes, and would be able to do a model merging, model distillation approach, leading to a
mm,
supermodel. And now you're combining this knowledge, which is from bipedals, humanoids, target recognition, kamikaze drones, leading to an intelligence which is not centralized to specific domains like whatever you're expert in. I'm great at mathematics. It knows
mm.
everything, leading to superintelligence. And once you're doing this global consolidation, that is your opportunity to be able to introduce more things which you see fit to control these machines.
I have to say, amazing, amazing. So
Sure.
this idea of superintelligence, I mean, you guys highlight this on your site and in different areas. Can you break it down real quick? Because it sounds like you have a couple different core features: foundational brain inspired AI models, adaptive AI agents, collaborative AI agents. So did you just basically give us the model that these are all, operating in, or is there something more that
Yeah.
we need to understand there?
So I started with software, which is traditional software, then standard AI, which has a human in the loop, which works well when it works, and then it needs an update. Then the next evolution would be adaptive AI, which is human level intelligence, which has the ability to be self aware and self evolve, right?
Mhm.
Then, whatever I'm telling you right now, you are able to learn. And that's also a component of human intelligence where we have the ability to teach each other, which we call collaborative intelligence. So in our case, also, one machine is able to teach the other machine so they can collaborate. Now, all of this thing is human level intelligence, self
Mm.
learning in real time, and then collaborative learning. So, and we are able to collaborate on similar domains. For example, you are able to understand well whatever I'm saying because we share some sort of common background of or interest. But if, let's say, I suddenly started speaking Chinese, you would not be able to understand that, even if I tried my best to explain to you. So we
Mm.
have the ability to learn and collaborate within specific domains, right? But machines don't really have that limitation till the point you are able to combine these different skills together. You can actually have a model which can have skills across very varied domains, leading to intelligence which is beyond human because humans are confined within certain domains, which is what we call superintelligence.
Beautiful, beautiful. It sounds like you guys are all at the frontier here. This is something that very rarely have I ever come across somebody who's specializing in this very domain. I'm wondering how did you get here? And then how do you then present this to the world in a way that's interoperable? That's something that other people can potentially build on, like turning it into a platform, let's say.
Right. So most of our work has been focused on defense, public safety, transportation, areas where the chances of you seeing something new is quite common. And that's why that's why we operate. So we have this platform called Kepler, where you can plug any sensor and it'll give you situational awareness. So there are pipelines built into that where it would say, okay, this is what I know. So it'll give you all the alerts for whatever you're trying to look for, be it weapons, people, guns, whatever you're looking for. And then it would say, oh, I'm looking at a new kind of target, which could be, for example, let's say I have a face detector, which recognizes eyes, noses, lips, and then it looks for assembly. It would say eyes need to be next to the nose needs to be next to the lip. Now, tomorrow, if I show you a face where I replace your lips with one of the eyes and in place of the lips, it would be able to say, this is something new, which has the basic building blocks of what a face should be, but the assembly is off. And that is what you observe in new kind of cyber attacks, new kind of weapons, new kind of vehicles. So there are these basic components which are changed to produce something new. And our system focuses on these kind of base component level representations and their assembly to be able to figure out these new kind of things.
Okay, so Kepler, you can basically plug in these other systems and it self-recognizes adaptations, modifications at scale.
Any sensor.
Right, any sensor. So then I also saw that you guys have something called Turing.
Yeah. So Turing is, please go on.
No, I was going to ask you, what is Turing in your own words?
So Turing is a platform which you mainly use for intelligence community. So Kepler is basically, like your head. You have eyes, nose, ears, so you can sense different ways and your brain makes sense of that and you're good to go, right? So whatever is in the brain, the machine learning components, they're built. Turing we use for intelligence communities primarily to get a sense of what is happening in the online world. Be it satellite data, be it social media, whatever that may be. But intelligence communities don't want to tell us what kind of AI pipelines they want to make. So Turing is a no-code platform which allows you to assemble these different kind of AI components on top of whatever sensor fields you have in a certain way so that you can get insights. And that's what they use. So it's basically no code, low code, adaptive intelligence for the online world. And that is where it becomes very, very important because data in the online world continuously keeps on changing. Hence the need for AI, which also adapts in real time rather than an offline upgrade.
So, okay, quick question. Maybe this might end up being like a circular question, but just for a moment, I'm wondering, okay, let's say you have a current generation of model that's already been created in a lab, tested, created guardrails, and you put into production and it's out there in the world. And now it's on its own autonomous. Now, I can't imagine that you suddenly stop creating these quote unquote foundational models inside the lab. So what do you do when you have these kind of autonomous systems out in the world to go out, bring them back in and update them accordingly? Is it really just that simple or is there a bit more complication?
So that's where our superintelligence node comes into play, where we are able to do online model updates, but it happens once in a while. When the system comes into the internet's connectivity, which is not always the case, especially for a lot of the defense applications where these models operate in silo, right? But if you think about what is the knowledge we are updating, right? So you taught it whatever you taught it in the lab. So you said, okay, your job is to go and identify vessels in the sea. So now you go and identify these vessels. Here is a subset of vessels you have. And then if you see something new, which is similar to one of these classes or a combination of these classes, then you say you have found something new. And that's all you're going to do. You're not going to do anything beyond that, right? Then if there's a model which knows how to walk, it knows how to walk. Then maybe there's a system which is in the water, which is mobile and needs to identify vessels. So it needs to know both skills, which is detection and moving the motors. So basically, these knowledge chunks which we are plugging into each system is a function of where these assets or digital life forms are going to operate. And if you need to upgrade where beyond a certain level they should operate, that's the knowledge you need to send. And that is also part of our guardrails, where you want them to operate in a confined space. And beyond that, they are limited. Unless you let them do whatever they wanted to do, they could. But similar to a human, someone will have to teach them at least the basic skills on the top of that which they could build. For example, you wanted to learn chess, you wouldn't be able to start right away unless someone taught you the rules, whether it was online or in person.
Right. Okay. So, like I said, it was going to be a circular question, but I just wanted to make sure I could fill that gap. So it sounds like you guys also have your own edge devices and applications. I saw that you guys have a tower, a camera, edge AI box, along with a couple other things. So I'm wondering, how do you guys end up deploying this for, let's say, a client that comes to the table that wants to put a system together? How do you think that through?
Yeah, I think so. For first is like this was need based. When we started building purely software and we wanted to embed it onto other people's hardware. And this, from a scaling point of view, business point of view, it's hard because you're totally dependent on the other person and their deployment rates and all that stuff. So that's how we started. First of all, building these assets which we could deploy. So that is how we started, and now we are deploying it primarily based on the application. For example, the tower is deployed at the border, and it needs to be its own self-contained ecosystem with its own power, with its own compute unit, and it connects to the internet only when it needs to send an alert. So that is a need at the border because these are remote environments, so we deploy it over there. We have another version of this model which is deployed in cities, which has a LiDAR. There are some towers which have cameras only. That does not work well because you run into privacy issues. And since it is LiDAR first, you're able to get away with that. So there was a need over there, and hence the specific selection of sensors. And then we move from now borders to cities to every office where you have a set of sensors, most commonly cameras, and you want to make them intelligent. So you just take our AI box, you stick the sensors in that, and you're good to go. Now, this is different kind of environments, different kind of deployments for different kind of applications. And then obviously we have applications where the sensor moves when it is on top of a car or on top of a drone. So based on whatever the application is, we are able to deploy them. But it mainly came about because we wanted to increase our rate of deployment with the end customer, which we were struggling with.
That makes sense. I can also imagine that building your own hardware is a difficult thing to do, especially when you're talking about embedded AI. So
It is.
maybe more of a recent question, macro issue question. How have these tariffs kind of like changed the way that you guys do business and the recent shortages that OpenAI, Meta, Google, Amazon, a lot of these players and a lot of smaller players too are all fighting over hardware. How are you guys able to execute these kind of like hardware solutions?
Yeah, supply chain is a big issue. If you're really handicapped by your models running on a GPU. So we have our models which run on a CPU or it can run on NPU, mainly the ones from Halo. Actually, you can run any model on a CPU. It's just going to be really bad. You can keep on quantizing it. You can run anything. So in our case, when we make the models really small, they can make mistakes, which can be either false positives or you can miss things, right? So that is where our self-correction, self-learning, adaptive AI comes into play. Because if we get a false positive, we are able to, with a single click, get rid of that false positive and similar false positives which might have come in the platform, allowing us to run everything with high accuracy on CPU-only devices. So since we are not limited to GPU devices only, we have been a little more flexible and maybe not affected that much by the supply chain issues, which is other companies.
Got it. Okay. So it seems like supply chain, it is an issue, but it also doesn't have to be as much of an issue if you know how to go about building the models and executing them properly. So maybe more of a technical question here. But it's still a relatively large question. There's the difference between large language models, small language models, and a lot of these aren't actually just language models. They're visual models. I think listen, I'm sorry, I'm not an AI engineer, so I'm not going to know the exact terminology, right? But you know what I'm talking about. Like they aren't exactly they might not need the resources that these other models that we know of need.
Yeah.
So is that what makes it possible to create the hardware that's a bit more attuned? You kind of already know what the model needs in order to put together the hardware.
I think, there are two lines of thought here. One is there has been this new trend of creating foundational language models, where the key idea is that you want to be able to learn language, understanding, or reasoning, coding, something else, all in one model.
Right.
Now, if I went for the same principle with our models, you would need to learn speech processing, vision processing, and motor processing within the same model. I feel like that's not necessary because that's not what the brain does. So the brain has modular cortexes, so which is like the visual cortex, auditory cortex, motor cortex, and the knowledge corresponding to these specific functions is specially localized in these specific regions. So the models which we use, they are similar. So they have these specific bifurcations, and in the input we sense that, okay, this is a auditory signal, so we will push it through the auditory cortex only. And since this architecture is more modular and localized, the number of parameters which you need to tune for a specific signal are much smaller, and you don't have to worry about dealing with a very bulky model and making sure that all the parameters are in sync and all that stuff, right? So that is something we don't do.
Right.
We do have combination of these sensors at the end, similar to the prefrontal cortex. But when it comes to processing the raw signal, we don't really consider all of them as a single architecture. So the architecture is different.
Such a smart way to go about it. I mean, that's how you guys got to, what is it, 1,000x resource efficiency?
Yeah, because the number of labeled examples you need to train are proportional to the number of parameters which you need to update using your supervised learning update. And the number of parameters which go through a supervised update are much smaller, primarily the later layers, similar to the brain. And the initial layers are low-level features, so we can handcraft them. And then you have mid-level features which go through unsupervised learning, and only the last layers which is supervised.
So it's this relatively complex, intelligent array of different types of models and learning that are just, in a way, like a symphony of intelligence, which is superintelligence, as you guys have put it together. In terms of use cases, it seems like you guys are doing things for defense, doing things for construction, doing things for even nonprofits. What are you most excited about right now?
I think the most exciting thing right now is primarily our deployments on the border. I think mainly that is the Scout Tower aspect. And that is because it's a big use case. It's a real use case, and it is affecting people in real life. And you can see the impact of that on national security and people in general, people living in Texas. But that's what I'm most excited about. And also because it has massive scalability tied to it. And the other thing which I'm always excited about is how does this technology get to every person? For that, it needs to be totally autonomous. And a lot of the use cases for that are in nonprofits, common people using it, right? And that is the work which we have done with nonprofits in India, which has led to rescue of a couple of children. And I think that's impactful work. And people are getting affected, impacted, benefited by this tech, which they have no idea about. And I think that's true innovation.
It really is exciting, the fact that you can have such an impact in such different areas, such different places, locations across the world. I'm wondering then, okay, what's next for you guys? You're working on the border, you're working on construction, you're working on all these things. So what's the vision of the next, let's say, 2 to 5 years?
Yeah, so the most of the work which we have done with sensors which are stationary or which have limited degree of freedom. For example, a drone which moves a certain way or a car which is moving on wheels. Right now, we are moving into more motor control, whether it's just robotic dogs or it's humanoids. And I think that is exciting because it has more uh, degree of freedom. You need to consider the responses which are coming from these each end points. to figure out, okay, questions of stability. So short answer is you're moving from just the perception world to the perception plus action world, finally moving towards our vision of digital life forms and bringing them into the real world.
So this upcoming wave that we know is going to happen maybe in like 5, maybe 10 years of humanoid robots, do you think you're going to be part of that wave? Is that a wave that you envision kind of riding
Yeah.
with Skylark?
So we are hoping to provide the brain for a lot of these humanoids, robotic dogs, any physical asset which is going to exist in our world, because it is extremely important for that machine to have the ability to sense something is wrong or different in my environment, and then have the ability to self-correct, self-improve for this new environment, then and there itself, so that your not asset is not stuck in a remote place waiting for an update over the cloud.
Right. You can imagine just walking along the road and then seeing a humanoid robot just standing there waiting, right? That would be a fun meme. So, okay. So in terms of like if that's the vision, kind of like what are the steps right now? What are you doing in the marketing, the sales, and then also the fulfillment to try to drive Skylark forward in that direction?
Yeah. So there are two dimensions. The first dimension is obviously the research dimension, where we continuously keep on figuring out ways to have better adaptation, better collaboration, all of those things. And we collaborate with different professors who worked with me during my time at DARPA, during my time at Stanford, MIT. So we work with them to improve our adaptive AI, superintelligence, all that aspect. The second aspect is the business aspect, which brings the money as to how do we insert this intelligence into different kind of physical assets so that they are able to actually provide an ROI to the end customer. So most of our focus right now has been on the AI towers, because I feel like there's a big demand for them, monitoring very large areas up to 2 miles will definitely lead to false positives, new kind of signals which you miss. And if you're able to correct for that right away, that's a very big advantage. So a
Right.
lot of our focus has been on that, and apart from the research piece.
So for these towers on the border, I can imagine them also being deployed on really large construction sites, maybe Stargate even potentially. Also maybe mines.
Yeah.
Interesting.
We also deploy them in prisons where you can have new kind of weapons. The prisoners make new kind of shells from whatever they can get their hands on. And that has the basic structure of how you're holding a weapon, but the front part can be quite different. So then you got to be able to figure out that this is a new kind of weapon they're holding.
Got it. I actually just recently saw in the news, I think it was on Nightline, or Dateline, I think it's called, where they talked about autonomous stealth fighters and autonomous subs, right?
Yeah.
And how they could run for months on their own, used with AI on board. Is that something like you envision your technology essentially getting deployed as?
So we are not into weapons yet. Most of the things we do are protective. They just observe and they alert, and the user takes its decision and they do what they want to do. But we have some things which we are doing which are on mission planning. And that again goes into our motor control. That okay, if you want to be able to, let's say, do a kamikaze operation using a drone, that is some work we are trying to do. And there is someone shooting at you from the ground because they can't be jammed. What path do you take so that now you're able to go and hit the target? So that's one example of what you just mentioned, where your adaptation is not just in the perception space that you see something new, it's also in the action space, rapid adaptation, so that you're able to complete your mission. So we have some form of work in that. We hope to do more in that direction.
So would you say that your ideal client, every business has ideal clients, would essentially just be the government?
So currently, yes, because our pitch with the government is we have systems which can adapt in a closed loop environment on the edge, which is generally defense and the requirements over there. Public safety is another target area we are focused on, primarily because a lot of these things are in the silo. But when we work with the commercial companies, for example, Coca-Cola is one of our clients. The key idea or the pitch over there is we are a system which produces the lowest number of false positives. because we are able to correct themselves. So I think over there, the false positive rate isn't that much currently because other companies are able to put their AI on cameras and the camera does not move. The environment is not as dynamic as other environments. So it's very hard for them to see our value proposition. In the case where we have been successful with Coca-Cola has been to monitor their plants using drones, which move at different speeds, different heights, and the chances of you seeing a varied environment is more. So we try to stay in the space where our key differentiation would come out, hence maybe these specific areas.
Understood. So the ideal clients, there's a very narrow place where you're specialized and you're basically best in class.
Yeah,
Which is exciting.
or best in class where the user can see us and the other person can't come and be like, well, we can also do it. Yeah, things need to go wrong for them to be able to see the value of our system because then you need to update that.
In a way, a good way to get the sale if things go wrong for them, but also in a bad way, things go wrong before you get called in. But it's good to hear that at least like you're out there. I mean, the site, the guys that you have. So we're rushing up on time, and I just wanted to give you the floor real quick for 2 minutes if you want, 5 minutes or 10 minutes. Just what would you like to say to the audience directly, and or anything that's really exciting or something that you're really passionate about that you want to share with everybody?
I think the thing we are most passionate about is how does this amazing AI technology get to a point where it can benefit everyone. So for example, my parents live in India, they speak Indian language, and my mom can use a lot of these systems, but obviously she's not an engineer. She was a school teacher. Her knowledge of this technology is limited, right? So if she uses Perplexity or ChatGPT, her experience is going to be vastly different from ours because she does not know how to use them, right? Same goes for security systems. So my hope or vision is to figure out how all of these amazing tools we have, whether it is language models or adaptive models, are able to benefit people on the ground who have no idea about this technology or how it works, but it can embed itself in everyday life of common people, everyday people, and aid them. And I think the way to do that is by embedding them into some sort of physical assets, phones or humanoids or self-driving cars or robotic dogs, so that they are able to benefit from that. Whether it is my mom who has trouble walking, if she has some sort of device which helps her walk, but also can adapt to her needs as she needs it, rather than a one solution for all. And I think that is a very exciting world where people can actually benefit from society, everyday people, rather than not just the elites of Silicon Valley or educated people. And I think that's a world we are headed towards. And I think it's a very exciting world.
I think so too. I mean, you guys, you and a lot of the other people on the podcast are driving the world forward in a lot of ways. And I'm so excited to see what you guys do because it's going to be completely different in 5 years. It's going to be a better world.
Appreciate it.
All right, Amarjot. Well, I really appreciate your time today. Thank you for taking the time for enlightening us about superintelligence and edge AI. And hopefully this is the first of many. Maybe you can come back for a panel with the others leading their edges, their niches in the AI space as well.
More than happy to do so. Thank you for having me.
Everybody. Well, that was another episode of the Genius Scale podcast with Amarjot Singh as founder and CEO of Skylark Labs AI. I'm not going to say I expect any of you to be in the government and key decision makers in a way that you can help Amarjot. But if you do know somebody, why not just reach out? It might help the world in a small, maybe large way. So until next time, you already know we buy and sell businesses, but we also help B2B tech firms grow. You can see details on our site. Till next one.
Thank you, sir.